Welcome to The Explainer. Today, we're diving into the surprisingly elegant mathematics behind one of the simplest shapes we know, the straight line.
I mean, think about it. How can you capture something that goes on forever with just a few simple rules? Well, we're going to explore the universal language that mathematicians came up with to describe any line anywhere on a flat surface. So, let's crack this code.
You know, everything in coordinate geometry really just starts with one thing, a single point. You can think of it like a unique address on a map, right? It's got its x, y coordinates.
Well, for that, we can't just guess. We need a really precise tool that lets us divide that line segment in a very specific ratio.
And here it is, the section formula. This is a huge aha moment in geometry. Honestly, this little formula is the secret sauce behind so much, like scaling objects in computer graphics or placing items perfectly in a video game world. What's really cool is how this one formula can actually be adapted. See, the formula has two flavors, and it all depends on where our dividing point P is. If it's inside the segment, tucked neatly between A and B, we call that internal division. But if the point is on the same line but outside the segment, extending past A or B, that's external division, and the formula just needs a tiny little tweak. Same logic, just a different location.
Okay, so we've mastered 2 points, but what happens when we throw a third one into the mix? This is where things start to get really interesting.
If 3 points don't line up perfectly, they will always form a triangle. It's kind of like the default shape for any 3 non-aligned points. And we can even calculate its exact area just using the coordinates of its 3 corners.
But what if those points do line up perfectly? Well, that's a special condition, and it's got a special name, collinearity. The triangle, it essentially flattens into nothing.
So this is the crucial part. We can actually prove that 3 points are collinear in 2 main ways. The first method, the triangle they form has to have an area of 0. I mean, it makes sense, right? If the 3 points are in a straight line, there's no height to the triangle, so the area is just 0. The second way, the steepness or the slope between the first and second point is exactly the same as the slope between the second and third.
And that idea of slope brings us to something really beautiful. Every single straight line has a unique identity, almost like a genetic code, and it's defined by just 2 key things.
The first part of its DNA is its slope. This one number tells you everything you need to know about how steep the line is and which way it's going. So if the slope is a positive number, you can just picture yourself walking uphill as you move from left to right.
And if it's negative, well, you're heading downhill. The bigger the number, either positive or negative, the steeper that climb or descent is going to be.
And a slope of 0, that's just perfectly flat ground. No rise at all run.
Now, the second part of a line's DNA is its intercepts. These are the exact addresses where the line crosses the main horizontal x-axis and the vertical y-axis.
All right, this is the moment we've been building up to. We've got the building blocks, the points, and we've got the DNA, the slope and intercepts. Now we're ready to write the master blueprint for any straight line out there.
So, what do you need to write the equation for any line? It's surprisingly simple. You only ever need 2 little pieces of information. One single point that you know for sure is on the line, and the line's unique slope. That's it.
And this is how they combine into this elegant, powerful equation called the point-slope form. This isn't just a formula, it's like the master key. You give me 1 point and 1 slope, you plug them in here, and bam, you can describe the entire infinite line.
Okay, theory's great and all, but let's see how all these ideas snap together to solve a classic geometry puzzle. So imagine a line segment stretched between the 2 main axes. Our mission, should we choose to accept it, is to find the equations of 2 new lines that shoot out from the very center, the origin, and chop that segment into 3 perfectly equal pieces.
The path to the solution is actually pretty direct. First, we use our trusty section formula to find the exact addresses of those 2 cutting points. Then, since we know our new lines go through the origin, we can instantly figure out their slopes.
And just like that, using only 2 core ideas that we've talked about, the section formula and the concept of slope, we can solve the entire problem. It's a perfect example of how these simple tools build on each other to do some really powerful stuff. So what's the big takeaway here? We've basically built the entire language of lines right from the ground up. We started with just a humble point, learned how to divide up segments, defined a line's unique DNA with its slope, and then captured it all in one single master formula.
This simple, elegant system is the foundation for a huge part of math, engineering, computer science, you name it, and it leaves us with a really exciting question to think about for next time.